A very good morning, students. Welcome to IIT NEET Foundation or Focus C program by Krishnaveni Talent Schools and the Mastermind Schools. So once again, I welcome all the branches along with your class 7th students for today's session. As you all can see on the screen and you are well aware, my subject is physics. We are in class 7th. Our ongoing chapter, which we have started yesterday, is gravitation. Today we are entering into the session number 2. So far we completed one session yesterday about the gravitation, where we learned about what is the gravitational force, right? What is gravitational force? What is gravity, right? Then what are the factors influence the gravitational force as per the Sir Isaac Newton, because he is the first person to observe the gravitational force, as you all know, when he sat under the apple tree, right? So gravitational force is nothing but force of earth. It is also called as gravity. So every body, whether it is falling towards the earth or thrown upwards, definitely it is attracted towards the center of the earth. Such a force exerted by the earth is called gravitational force, or simply gravity, force of gravity. And this force of gravity mainly depends on two factors, right? One is mass of the bodies, and second one is distance between the bodies, right? Mass of the bodies and distance between the bodies. These are the two important factors where this value depends, this effect force depends, right? So that is this. To explain about these two factors, Sir Isaac Newton is given the various examples where this gravitational force affects. Then he proposed the very popular law, Newton's law of gravitation, or universal law of gravitation, right? So today we are going to discuss about this universal law of gravitation and some important terminology related to this, right? So this is here what we learned in the last class about the gravitation and gravity. And of course, we just introduced about the universal law of gravitation or Newton's law of gravitation, because you all know Newton's law of motion, 3 types. This is also one of the important factor for that. See here, there are two bodies of masses M1, M2, or capital M, small m. One is a big body of capital M, another one is a small body of small m. These two are separated by a distance r. Right. So what is this statement says that every body in the universe attracts every other body. Every body in the universe attracts every other body with a force of gravity, right? So that force between the two bodies, right? The force is called gravitational force. It is only attractive force, gravitational force, not repulsion, no repulsion, only attractive. So like this, when you are separate two bodies of M and M, or you can get M1, M2 also, no problem. Then what he says that as per this law, F is equal to G into M1, M2 by R square, or you can write as MM by R square also, if they are given mass are MM. Means the gravitational force between any two bodies is directly proportional to their product and inversely proportional to their square of the distance. Whenever the mass increases, gravitational force increases. Whenever the distance increases, gravitational force decreases. Right. From that, you got the law which is given by F is equal to G MM by R square, or M1 M2 by G into M2 M1 M2 by R square. So what is the G? G is the constant taken. That is called universal gravitational constant. It is constant for every body, any planet, not only for Earth. The value is constant, which is given by 6.67 into 10 power minus 11. Newton meter square by kg square, which is the unit of G. So the G is the constant introduced by Newton, which is named as universal gravitational constant. It's given here, capital G. Right. So from this formula, you can write capital G is equal to, from this only, take R this side, Fr square by M and M. From that, you got that unit, Newton meter square by kg square. Right. So that is a formula given here. Everything is clear. There is nothing hidden. And the units are Newton meter square by kg square. This is called universal law of gravitation or Newton's law of gravitation. It's a very, very famous law for which is restricted for the Earth. But same thing can be done for the other planets also, which is explained by the Kepler. Johannes Kepler will discuss later. Okay. So before going for the further explanation about the Newton's gravitational law, let me show you one video on this same. And after watching the video, we'll come back and we'll continue with the characteristics of gravitational force, right? Just animated video, you can enjoy.
Gravitational force acts between any two objects in the universe. One easy way to demonstrate the effect of gravitational force is to suspend a horizontal scale with two masses at the end, as shown. Now, quickly place two large masses next to the mass of the scale. If you wait and observe, you can see that two small masses will move closer to the big masses, and eventually they will stick together. This force of attraction happens due to the gravitational force. It looks interesting, right? Let's learn a few more details about the universal law of gravitation and how Sir Isaac Newton discovered this very important law. As we all know the story, an apple fell down from a tree, which started Newton thinking.
See how beautifully explained.
Let's assume there is one more apple tree that is far away from the current tree, and an apple falls from it as well, as shown. If you analyze this way, it is clear that objects fall to the Earth in a radial direction, or the Earth attracts the objects radially towards the center. This observation was the turning point in the discovery of the universal law of gravitation. Newton realized that the Earth does not attract the objects just down, but it attracts the objects radially towards its center. It's logical to conclude that, in a similar way, the Earth is pulling the Moon radially towards its center with an attractive force. Similarly, the Sun as well is attracting the Earth towards its center with a certain force.
See, everywhere is applicable.
Now let's move away from these rounded objects. With the same logic, this car will attract this book towards its center of mass. Similarly, this book will attract this car towards its center of mass with a certain force. According to Newton's third law of motion, these two force values should be equal.
Action and reaction.
In short, all the objects in the universe attract each other with a certain force. This is the universal law of gravitation. Now, the next challenge. Newton wanted to derive an equation to predict the magnitude of the force which arises due to the universal law of gravitation. Newton's intuition told him that the effect of gravitational force would dilute with distance. But to what extent? To get an answer for this question, he looked at the Moon. The Moon is also attracted to the Earth due to the same gravitational force. However, the Moon doesn't fall to the Earth because the centripetal force required for the Moon's circular motion is supplied by the gravitational force. People at that time already knew the Moon's angular speed and the distance between the Earth to Moon. Based on this force balance idea, Newton calculated the centripetal acceleration of the Moon. The force acting on the apple near to the Earth's surface can be easily calculated by measuring the apple's acceleration. The value of this acceleration is 9.81 meter per second squared. Newton compared these two acceleration values with the distances from the center of Earth. Can you spot any connection between these four numbers? If so, congratulations! Anyway, Newton was able to find out a definite connection between these four numbers. Divide the acceleration values. Now, take the square of the distances and divide. Surprise! The resultant values are very close. This means the gravitational force is inversely proportional to the square of the distance between the center of the objects. What a brilliant deduction! The next question is, do the objects' respective masses have any connection with gravitational force between them? Newton had already derived the equation for an object's acceleration during this period, and it is a common observation that when the force arises due to gravity, the value of acceleration does not change based on an object's mass. Therefore, the value of force due to the universal law of gravitation should be a factor of the mass, so that when you find out the acceleration by dividing the mass factor will get cancelled. Likewise, we have to include the mass of the second object as well in this equation, in this case, the Earth's mass. This is the expression Newton derived to find out the force due to the universal law of gravitation. He introduced a constant called the gravitational constant and made it a proper equation. According to the universal law of gravitation, all the objects in this universe attract each other. In this case, the Earth attracts the apple with a force value defined by this equation. The apple also attracts the Earth with the same force value. However, the Earth doesn't move to the apple because when you divide this force by the mass of the Earth, the acceleration value becomes negligible. The case is the same with every other object in the universe. It's somewhat impossible to believe, right? Are all the objects in the universe really attracting each other? We find this idea difficult to believe because we live in a world where frictional force is always present. Just imagine a long, frictionless room with no object in it. Now, introduce 2 blocks on the floor. If the frictional force between the object and floor is 0, you would see the blocks move toward each other due to the gravitational force and finally collide. Of course, this was a hypothetical experiment. A more realistic experiment to visualize the effect of gravitational force would be placing 2 heavy balls near a hanging 2-ball arrangement. If no objects are near them, you'd observe that slowly the small balls would move to touch the larger ones. Even though Sir Isaac Newton derived the equation for the universal law of gravitation, he didn't find out the value of g. Many years later, an English scientist named Henry Cavendish came up with a clever idea to determine the value of g. His experiment was very similar to the example we saw earlier. The only difference is that his setup was able to attain a balance force between the force due to gravity and the string's torsional force. You can see clearly that when the torque produced by the torsion of the spring is the same as the torque due to the gravitational attraction force, the balls balance.
So from that,
Using this twisted angle at the balance as an input, Cavendish calculated the value of g for the first time, that too quite accurately. We hope you now have a clear...
Right. So one more is there, we'll complete that also, we'll see, and we'll next. This we'll discuss after that, okay. So what clearly explained in the video is, what is the Newton's law of gravitation and what is the universal law of gravitation, right? Are clearly explained there. So according to Newton, the force, gravitational force mainly depends on mass and distance between the bodies, which you can see clearly in the, right? So when you come to the part of characteristics, so all we have seen what is the value of g, what is the unit of g, everything. But now we come to characteristics of the universal. So gravitational force between the 2 bodies or objects does not need any contact between them. It means the gravitational force is action at the distance force. There won't be any contact also. See, when you are dropping a body, there is no contact between body and earth, but still it is attracting. It is a non-contact force. Okay, then gravitation between the 2 bodies inversely proportional to the square of the distance between them. Hence, the gravitational force is an inverse square force. Right? It is an inverse force. So that is the characteristics are given here. So when you move to the further explanation of the Newton's gravitational law, some more are there. So the gravitational force between 2 bodies or objects of the relation paid. If an object A attracts the B, force F1, then B attracts with the force F2. Then F1 is equal to minus F2 as per the Newton's third law of motion. Action is equal to minus reaction. Okay? Then free fall. A falling of the body or object from the height towards the earth under the influence of gravitational force of earth with no other force acting on it is called free fall. We can call, suppose when you are dropping the pen, what happens? It is coming down. I am not applying any force, simply there is no contact also. So this is called freely falling body or free fall body. Without any direct contact, there is no other force is helping this pen to come down, only gravitational force. Right? So when you some instructions are note is given, the acceleration of the object falling free towards the earth does not depends on the mass of the object. Hence, same body, it is same for the bodies of any mass. Very important point which is proved by Galileo. Suppose when you take a cork ball and take a plastic ball, when you drop the both of them, on both bodies, gravitational force is same. So body reach at same time. They're supposed to reach at same time. They're supposed to reach at same time. Why you are disturbing Ramnagar branch? So they reach at same time until if there is no air resistance. This experiment is done by the Galileo in Leaning Tower of Pisa in Paris. From the tower, he dropped the feather and coin and see that both of them are coming. Even vacuum tube also done. Means gravitational force on the body is irrespective of the masses. It does not depends on the mass. So, free falling body has the acceleration equal to the acceleration of the due to gravity. So see, actually it is at rest. There is no velocity for the body, pen. But when I'm dropping, it is attracted towards the force with the acceleration. That acceleration is called acceleration due to gravity, which is denoted by small g. The acceleration produced in a freely falling body due to gravitational pull of the earth. An acceleration produced by a freely falling body due to gravitational pull of the earth is called acceleration due to gravity. You know acceleration, rate of change of velocity. But that is produced by the earth gravity, that is called acceleration due to gravity, is given by value g. So g value on earth is 9.8 meter per second square. Earth. This value changes, not take capital G. So G value on moon, if you see, 1.67 only. That is, these two are 1 by 6. G value of moon is 1 by 6th of G value of earth. 1 by 6. Similarly, when you see G value of sun, 27.4 meter per seconds. And G value on Jupiter, as size increases, the value increases. It is 29 meter per second square. So the G is nothing but acceleration. The acceleration produced in a freely fall body due to gravitational pull of the earth or pull of the any other planets. So this value is same on earth everywhere. Whether you are in Hyderabad or Visakhapatnam or America or Australia or Colombia, no matter. The value is approximately 9.8. There may be slight variation, but it is a constant value. Similarly, on moon, it is 1.67, which is less than 6 times less than that of earth. When you go to the sun, it is 27.4, or Jupiter, it is 29 meter per second square, which is almost 3 times greater than the earth. Suppose your weight on earth is 60 kg. Imagine on earth. When you go to the moon, your weight becomes 10 kg only. 10 times less because G value is 10. When you go to Jupiter, your weight becomes 180 kg. You feel very heavy because of the gravitational force. Of course, we cannot go to sun. If you go to sun, you get only ash. Right? So the G value changes. That G value is called acceleration due to gravity. So before the explanation about the acceleration, it's a very big topic. I'll show you one video on the acceleration due to gravity. Then we'll move to the topic. Okay.
Module. You will learn about acceleration due to gravity. When you throw an object up, it comes down due to gravity. When an object, such as a boulder, is pushed from a height, it falls to the earth. Such an object is said to be in a free fall.
Free fall.
An object is in free fall when it falls to the earth under the sole influence of gravity. A fruit falling off a tree or a sandbag thrown off a hot air balloon hurtles towards the earth in a free fall. However, a parachutist is not in free fall, since the parachute reduces the effect of the gravitational force of Earth. A body under the influence of Earth's gravitational field can be a body dropped from a certain height, like a ripe fruit falling off a tree. A body thrown vertically downward from a certain height with some velocity, such as a ball thrown down by a boy from the 5th floor of a building, or a body projected vertically upward. For example, a stone thrown vertically upwards. Objects in free fall move only in vertically downward direction. However, their velocity changes as they fall. A change in velocity results in acceleration. The acceleration of a freely falling body due to the gravitational force of the Earth is known as acceleration due to gravity. Acceleration due to gravity is denoted by the small letter g and is measured in meter per second square. How can you determine how long it will take for an object in free fall to reach the Earth from a specific height? To perform such calculations, you need to know the value of acceleration due to gravity. Let us now derive the expression for acceleration due to gravity, g. Consider a freely falling object of mass m. Let the capital letter M denote the mass of Earth. D be the distance between the free-falling object and the center of the Earth. And R be the radius of Earth. Since the object is in free fall, the gravitational force F on the object is the product of its mass m and the acceleration due to gravity g. Let's call this equation 1. The gravitational force F between the Earth and the free-falling body can also be calculated using Newton's universal law of gravitation.
How to find the small g value they are
F
explaining.
is equal to
It's already we have
g
seen.
multiplied
First one is
by
Newton's second law of motion.
m
The second
divided
one
by
is
d
the
squared.
Newton's universal gravitation law. When you combine these two,
When
you
the
get the
object
g
is
value.
near to or on the surface of the Earth, the distance d is taken as
R,
equal to the
radius of
radius
Earth.
of the Earth, r. Let this be equation 2. By equating
Both are force
1
only. You
and
can
2,
equate them.
we can calculate the acceleration due to gravity as g is equal to
That is the value for the
G
form power
multiplied by M
small
divided
g.
by R square. Since the Earth is not a perfect sphere, its radius is maximum at the equator and minimum at the poles.
Wrong.
Hence, the acceleration due to gravity is greater at the poles than at the equator. This difference is negligible for bodies on Earth. To calculate the value of acceleration due to gravity, G, we need to
Values, if you
substitute the
substitute
values
mass of the
of
Earth, mass of the
universal
body, you can get it.
gravitational constant,
See,
G,
gravitational constant is 6.67.
mass of the Earth,
Mass of the Earth
M,
6 into 10 power 24 kg.
and radius of the
Radius
Earth
of the Earth.
are
Substitute
in
the
the
value to get
expression we
9.8.
derived. On substituting and simplifying, we find that the value of G is approximately 9.8 meter per second square. Acceleration due to gravity at a place on Earth is the same for all bodies
See there, metal is given,
irrespective
wood is
of their
given.
masses. Let's use two identical objects with different masses to verify this statement. Drop a metallic ball and an identical wooden ball from a height. Do you notice that both reach the surface of the Earth simultaneously? Since the mass of the metallic ball is greater than that of the wooden ball, the force of gravity on the metallic ball is greater than that on the wooden ball. However, it doesn't seem to make the metallic ball fall faster than the wooden ball. This proves that acceleration due to gravity on Earth is the same for all bodies, irrespective of their mass.
Right. So acceleration, that is about the acceleration due to gravity. Right. So in next class, we'll discuss more about the acceleration due to gravity and its effects and how it is useful, and finally followed by our Kepler's laws. That is about other planets. Right now we are discussing only about our Earth. Right. Now when you come to the synopsis 3, we are going to discuss about the other planets also, where Kepler studied about the gravitational force of other planets and proposed the Kepler's laws of planetary motion. Okay. So you can have wonderful home task, go through the material and try to solve the level 1 questions, level 1 and level 2 of this particular topics what we covered so far. We covered so far about what is gravitation, what is gravity, universal law of gravitation, and acceleration due to gravity. That is capital G and small g, very important. And go through the materials and solve the worksheets given at the end of the chapter. Right? So thank you, students. Have a wonderful day. Thank you.